X-ray diffraction allows precise chemical compositions, phases and structures to be determined in crystalline material. In addition, X-ray diffraction can help to determine microscopic stress conditions, for instance in a material or a ceramic. The internal structure of a material can be discovered best when that material is available in a crystalline form, that is to say, when the atoms are arranged in a regular, repetitive pattern. The incident X-ray light is reflected, or more correctly, diffracted from the atomic planes of the crystal invisible to normal light. While the direction of this diffracted beam depends on the distance between the atomic lattice planes, the intensity of the diffracted beam is a function of the number of electrons, that is to say, the atomic composition of the material. The structure of the crystal can be determined unequivocally by measurement and mathematical treatment of these two beam characteristics. The most important advantages of synchrotron radiation in X-ray diffractometry consist in the highly parallel radiation, which allows the atomic layers in a structure to be resolved with considerably more precision, and in the high intensity of the beam, which allows very small crystals to be studied of materials difficult to crystallize. Scaling down and condensing circuit elements on a microchip is a permanent objective of research and development in the electronics industry. For this purpose, the properties of the manifold semiconductor layers and their interactions must be known in detail. Properties such as the perfection of a crystal, the micromechanical stress, and the layer structure determine the smallest usable dimension of circuit elements, and in this way such functional characteristics as the power consumption, switching rate, and service life. Measurements of X-ray diffraction by the layers of a gallium arsenide semiconductor laser show that there is a mismatch between the surface and the substrate, that is to say, the distance between the atoms of the cadmium selenide and cadmium sulfide layers differs by a few percent from that of the gallium arsenide substrate layer. Measurement of the X-ray reflection curve provides detailed information about the matching and completeness of layers. The position of the reflection changes towards a lower value as the distance between the atoms increases, while the width of the reflection becomes larger with decreasing order. In the case of the semiconductor laser, the data show that the atomic order in the surface deteriorates as the distance from the substrate layer increases. Possible uses of X-ray diffraction range from the determination of the atomic structures of new types of drugs to studies of chemical reactions in catalysts, to the characterization of the microscopic structure of high-performance ceramics. In all these applications, the use of synchrotron radiation enables a more profound knowledge of material structures to be gained and more reliable information to be acquired about materials' properties and materials' behavior.